What if a model trained without a single label could still learn to understand objects and do segmentation? This is emerging properties in self-supervised vision transformer. What you see on the screen is not the result of supervised learning. It's pure emergence from self-supervision. No labels, no segmentation masks, just a vision transformers in which they call it a dino model. This model only cares about the objects in the image, like this bird, this toothbrush, and many more. For more example, in here we can see dino. Without even telling where the dog is and where to focus on, it only pays attention to the dog. Even when half of the ship is behind the sea or horse is below the crest, it is not a problem for dino. Dino is built to address VIT problems, in which VITs need a large amounts of labeled data, and also their features are not unique, especially compared to CNNs. So, what if VITs are missing their full potential due to the supervision? Here is where Dino comes in. Started from the success of NLP, which is thanks to self-supervised learning concept. And Dino wants to adopt this along with knowledge distillation. In knowledge distillation, we have a teacher model like VITL, which is strong model but slow, and a student model like VITB, lighter and faster. The goal here is to transfer knowledge. Now, Dino takes this idea further. It's a self-distillation, simple, efficient, and completely unsupervised. Now, let's just talk about Dino. Here, we take two different views of the same image and feed them to the networks. The softmax here give us some probability scores for different classes. Do we have any classes? The thing is we don't have any labels, but we should estimate how many labels do we have. By having these, we can apply our loss function and distill some knowledge from teacher to student. But one thing to note here is that teacher is not pre-trained, and it is not stronger than the student. It has the exact same architecture, but somehow it should be stronger. So you might ask, why should this teacher be better? Well, that is because of a concept called multi-crop training. In multi-crop training, we can perform two different kinds of crops. The first one is global views, and the second one is local views. Unlike students, teachers use only global views that have more information, which yields a better representation. Obviously, when students receive global views, it has the potential to be the strongest, but given multiple inputs, teachers should outperform because they always receive global information. The next question is, how can we train teacher? First, they copied student weights to the teacher during each iteration, but the accuracy is very low. Then they tried doing this again, but it didn't change anything. So they copied the student weights after each epoch and got high accuracy. By doing this, hopefully the student moves in the right direction. So the slower we change the weights, the better results we achieve. And that's the reason why they are using momentum in the end, which is this exponential moving average formula. And if we look at the learning curve, we can see teacher and student are evolving. But if you want to try this by yourself, your model might collapse. How to avoid this collapse? So there are two scenarios of this collapse that might happen. The first thing is teacher and student might produce a uniform distribution along all dimensions. This can reduce the loss function because on the cross entropy loss, it reached the minimum. But this is not what we want. The other thing is the output will be dominated by only a single dimension. So how can we solve these two issues? For the first problem, we need to sharpen our output by adding temperature to the softmax formula. Assume that this is our logits. Here is the original softmax output. After lowering the temperature, we get these two features. But doing this would get the second problem. And how we can avoid this? We can use centering operation, which is add a by C to the teacher logit before passing it to softmax, and this C bias term is just some exponential moving average of previous C. By adding this C, we can smooth out the distribution. That's the whole idea behind Dino. And now we can just talk about the results. Here, Dino outperforms other self-supervised methods. Over the other methods, Dino can improve accuracy by 3.5% to 7.9%. It is also being the top while being 10 times smaller and 1.4 times faster than others. In summary, Dino enables label-free training with strong semantics features, and the trade-offs? It's memory heavy, a bit unstable, and sensitive to hyperparameters. Thank you.